Hi guys, Justin here from chemistrynotes.com, and we're starting a new section today, section 14, and it's called acids and bases. So section 14 is kind of like a chapter 14 in your textbook, and I call my chapters sections, as you know. So this is our 14th, section 14, acids and bases. Let's just get started, shall we? So in the last section, section 13, chemical equilibrium, we discussed the fundamentals of chemical equilibria, right? That's where you start with reactants or even start with products and they equilibrate or reach this dynamic steady state where we have reactants and products coexisting where the forward reaction and the reverse reactions are equal, right? So in section 13, we discussed those fundamentals. Those are fundamentals of chemical equilibria. And in this section, section 14, acids and bases, we're going to apply those applications to acid-base reactions and systems involving H plus transfers or proton transfers. Now, we're going to utilize the stuff we learned in section 13 a little bit later in section 14. Today's video is more or less just an overview of acid-base chemistry and different types of acids and bases. So let's just go ahead and get started here with our second bullet point. Acid-base chemistry is important in a wide variety of applications. Some examples that you see in everyday life or in environmental chemistry are acid rain, blood pH, aquariums, pools, etc. Now, very, very generalized, acids are sour. Things like lemon juice or vinegar are examples of acids. An everyday example of a base would be soap or Drano. And bases, which used to be called alkalis in the old days, bases taste bitter and they tend to be slippery. Now, I want to give you some definitions of acids and bases. The first set of definitions is Arrhenius acid and base, and the second set of definitions is Bronsted-Lowry acids and bases. So an Arrhenius acid is a substance that produces or releases H plus ions, which are the same thing as protons, by the way. An H plus ion is just a proton. Arrhenius acid, a substance that produces H plus ions in aqueous solution. Okay, it's got to be an aqueous solution. Arrhenius base has to be an aqueous solution again, but an Arrhenius base is a substance that produces OH minus ions in solution, specifically in aqueous solutions. So the Arrhenius acid and Arrhenius base definitions, the Arrhenius acid releases H plus. The Arrhenius base releases OH minus. But we're kind of confined to the fact that we have to be in aqueous solution. Now, in a general chemistry class, like in a lab and stuff, that's usually not that big of a restriction. Mostly everything we do is in aqueous solution. Everything is water-based. But from a greater point of view, we need to have a better definition of an acid and a better definition of a base. That's where the Bronsted-Lowry acid and Bronsted-Lowry base definitions come in. So I got a little star there by Bronsted-Lowry acid. And it says it's a substance that is a proton donor or an H plus donor. You notice that's essentially the same definition as an Arrhenius acid. It releases or donates protons, H plus ions, to the solution, but it doesn't have to be an aqueous solution. Bronsted-Lowry base, the second star there, a substance that is a proton or an H plus ion acceptor. Okay, so that's a different definition than the Arrhenius base altogether. So a Bronsted-Lowry acid is going to donate H plus into solution. Who accepts it? The Bronsted-Lowry base accepts it. Okay. Here's an example. This is an example of water acting as a base because what's it doing? It's going to accept H plus ion from hydrochloric acid, HCl. Now, you notice that it's kind of an aggressive acceptance, right? He's going out and grabbing that H plus, but you have an H plus acceptor, Then you have an H plus donor, and this is an acid-base reaction. So if you look at the reaction side, you see that we have a hydronium ion, H3O plus, and then we have the Cl minus ion, -1. And those are the products. Okay, so this is your typical acid-base reaction. In this particular example, the H plus acceptor, water, H2O, water is acting as a base. We'll learn in a few videos from now that water can also act as an acid, by the way. But H2O is acting as a base, therefore it's a proton acceptor. You would expect to see H3O plus as a product, and we do. With HCl being my acid, it is a proton or H plus donor. That's why we see Cl minus as a product in that last equation. So in general, using that last equation, that last specific equation, we can write a general equation, which I'm going to put a box around. HA, my acid, plus H2O, liquid, these guys react, and I get H3O plus, my hydronium ion, plus A minus. Okay, so if HA is my acid, A minus on the other side of the equation is my conjugate base. If H2O is my base on the left-hand side, after it accepts its proton, H plus, it becomes H3O plus. That is my conjugate acid on the right-hand side. So the definition of a conjugate acid is simply something on the right-hand side of the equation that's formed when the protons, or when a proton, H plus, is added to my base. Conjugate base is what remains of the acid after the proton or H plus ion is removed. Okay, they look very similar, right? An acid and its conjugate base kind of look similar. One's just missing an H plus. The base and the conjugate acid looks similar. One's just missing the H plus. Or I'm sorry, one has an additional H plus. All right, we're going to make 4 notes. The fourth note I'm going to make is actually the most important. But HA and A minus above are conjugate acid-base pair. H2O and H3O plus above are also a conjugate acid-base pair. All right, so that one reaction has 2 conjugate acid-base pairs. All right, those are the notes 1 and 2. Note number 3, the above reaction that I just put 3 stars by because of its importance, the above reaction is essentially a competition for the H plus ion. It's a competition for the proton. Okay, if you look at this reaction, we have a double-headed arrow, and the double-headed arrow doesn't lean towards one side or the other, but essentially your equilibrium is going to lie, and we'll get to this, it's going to go away from the stronger acid and stronger base. More on that later. All right, so I'm still continuing with note number 3 here. I'm going to draw my equilibrium expression for that reaction. Ka equals products over reactants, right? So the concentration of H3O plus times the concentration of A minus all over the concentration of HA. You notice I left out water. That's because water is a pure substance. It's a liquid, right? Equilibrium expressions from section 13, we only include aqueous and gaseous reactants and products. Now, Ka equals H3O plus times the concentration of A minus divided by HA, which is also equal to H plus times the concentration of A minus all over HA. Just a little note here. For all intents and purposes, you can assume that the concentration of H plus is equal to the concentration of H3O plus. We've just removed the assumed H2O from the H plus ion. So I have a bullet point here. It says, if H2O is a much stronger base than A minus, then the equilibrium lies to the right. We have a larger Ka value. So on the previous page, I had that boxed up equation, right? H2O was my base on the left. A minus was the conjugate base on the right-hand side of the equation. So if H2O is a much stronger base, equilibrium shifts away from the stronger base, and so therefore equilibrium lies to the right. If equilibrium lies to the right, we have a larger Ka value, right, from section 13. So why does equilibrium lie to the right? Because H2O is quote-unquote better than A minus at grabbing or accepting a proton in the reaction. Now, the opposite, second bullet point. If A minus, that's the base on the right-hand side, we have it labeled conjugate base on the right-hand side of the equation from the last page of notes. But just because it's called conjugate base doesn't mean it's not a base. So if A minus is a much stronger base than H2O, then the equilibrium lies to the left, away from that stronger base. So why does it lie to the left? Because being the stronger base, A minus, it's better at accepting a proton from the guy right next to him, which is H3O plus, and the reaction moves to the left, smaller Ka value, all right? So in any situation where we have like an HA plus H2O yields H3O plus A minus, that equation that has a box around it on the last page of notes, we will always have the strong acid and strong base on the same side, and equilibrium will always lie away from that side. Why? Because a strong acid and strong base are better at their job, which is transferring H plus between each other and causing the reaction to occur. All right, note number 4. Because H2O liquid is not included in the equilibrium expression, the Ka has the same form as a simple dissociation reaction for HA. Let me explain to you what I mean. First, let me reread this. Because H2O liquid is not included in the equilibrium expression, the Ka has the same form as that for a simple dissociation reaction. This reaction that I'm writing right now, I'm putting a box around. The only difference between this and the reaction I had a box around 2 pages of notes ago is that on the left-hand side, there's no H2O liquid. And on the right-hand side, H3O plus is now instead called H plus. But a Ka for this is still concentration of H plus times concentration of A minus all over the concentration of HA. Same equilibrium expression, right? So don't forget the role of water though, H2O liquid. On the left-hand side, really we also have a little plus H2O liquid in there. On the right-hand side, that H plus is essentially H3O plus. All right, but we can abbreviate things and write out simple dissociation reactions for this, okay? All right, next video, video number 2, I'm going to continue with this Bronsted-Lowry acids and bases, talk more about these types of reactions, all right? So stick around for that. It's coming up next.